Hello, everybody. Welcome back to the second part of associative memory. So here we are going to discuss about the match logic that is there for each cell of associative memory. So as we are aware, we have the argument register. As we had seen in the previous class, we have the bits of the argument register, that is A1, A2 up to AN. And then we have the key registers bits K1, K2 up to Kn. And then we have the words of memory, that is C11, C12, and so on. And also the bits of the match register, which we denote by using the M1, M2 up to MM. So now, as I have mentioned before, that each cell for storage, they use the flip-flop Fij for the storage. So Fij refers to the content of the cell. So with this information, let us start and let us look at what is there in the match logic. So when we are talking about matching a word I, say I have a word I. So a word I will match the contents of the argument register A if A1 is equal to Fi1, A2 is equal to Fi2, An is equal to Fin. That is, all the bits are same. All the bits of the argument register, the corresponding bits of the argument register and the flip-flops in a cell are same. So this is my A. So I have A1, A2 up to AN. And say this is my, in my associative memory, this is my ith word. So these are the flip-flops Fi1, Fi2 up to Fin. So it will be equal, if this is equal to this, okay, then this is equal to this, and this is equal to this, and all corresponding bits are also matched. Again, I'm not considering the key register immediately. We will take into consideration later. So can I write this match logic as something like by this Boolean function, xj is equal to aj Fij plus aj dash Fij dash. Okay, so I can write it like this. That means A1 must be equal to Fi1, A2 is equal to Fi2, and for this, what is j? J going from 1 to n. So xj would be match for first word, okay, x for the first pair of bits, x1, x2, x3, x4. Okay, so I can say the whole, I think it is better I give an example here. So let's say the word I am searching for is in my argument register is 100111001. So this is there in my argument register, and the ith word, let's say some particular word of this is 100111, same word. I want to see if this is a match. So for this, can I write, let's say, what is x? This is x1, this is x2, this is x3. So I'll have x4, x5, x6, x7, x8, and x9, because it's a 9-bit word. So I have all these x. So what is x1? X1 is 1 if A1 is equal to Fi1. Okay, and it is 0 if it is not so. 0 otherwise. And this can be captured using this particular Boolean function. So I can express this particular logic using the given Boolean function. So using this Boolean function, I can represent if there is a match, if the bits are matching or not matching. So if I just take the first, let's take the first bit. Here I have first bit. This is first bit in A is 1. First bit in I is that is the first bit of word I is also 1. So if I put it in this, x1 is, that is 1 and 1, or aj dash, that is 0. aj is this one now, and fij dash is this one. So this is also 0. So what do I get? I get a 1. Okay. Let's just change this a little bit. Let us consider this. Let's say that this is a 0. So I'm comparing this to now. So when I'm comparing this to, I will see here, this would be x5. So x5 would be aj, which is 0, and fij, which is 1, or that is the complement of this, which is 1, and the complement of this, which is 0. So what do I get? I get 0 or 0, which is 0. So x5 would become 0. So that means these two bits are not matching. So this particular Boolean function gives me whether it's a match, whether the corresponding bits are matched or not. But then in order to match the entire word, I don't need to match only the individual words. Only the individual words will not give me whether the whole word is a match or not. So to get that, what I need is that all the bits that you can see here, all the bits must be equal to 1. So this we can represent it using a function like this. Mi is equal to x1 and x2 and x3 and go on up to xn. So all n bits must be 1. So I'm using the n function for this. And this, don't you think this will give me 1 if all the bits are 1? If all bits match. Okay. So I'm assigning this to mi. What is mi? Mi here is the corresponding bits of the match register. So the corresponding bit of the match register will be set to 1 only if it's a match. So it will be a match. It will be a match only if all the bits x1, x2, x3, x2, xn are 1. And I get it from this particular function. So this is my Boolean function for comparing the words, the bits of the argument register and corresponding words in the match register. So I can write it now like this. Mi is equal to aj fij, okay, or aj dash fij dash, okay. That is the product of all this. Sorry, I'll have to move this a little bit. This is going to be the product of all of this. So mi is equal to the product of all of this, you can see. So for j going from 1 to n. So I can write it like this. Or if I write it in the long way, mi would be equal to a1 fi1 or a1 dash fi1 dash, a2 fi2 or a2 dash fi2 dash, so on for the nth word, an fin or an dash fin dash. So this is the match logic. But then we have not yet considered the key register. So now let us look at the key register. So when we include the bits of the key register, that is K, in that case, now we have to match only for those bits for which the corresponding bit Kj is equal to 1. So let me write it here. Match only the bits for which Kj is equal to 1. Others we can ignore. So this we can write it again in this format. That is xj or kj dash is equal to either xj if kj is equal to 1, or it is equal to 1 if kj is equal to 0. Let's see what it means. So here I'm going to OR the xj. Xj is what? Xj will tell me if the corresponding bits are matching. If the jth bit is matching. Then if we take into consideration kj dash, then the kj dash here would give me kj if the bit is 1. So if the key register bit is 1, then I'm going to match. That's why I get an output of kj. And if kj is equal to 0, if the corresponding bit of the key register is equal to 0, then it does not matter whether it is a 0 or a 1. So we put a 1 here, because remember, this is going to be an AND of all of this. It's an AND of all the x's, all the xj's. So if I am going to ignore something, then I better make it a 1. Otherwise, if I make it a 0, this AND of this, all the x's will not be equal to 1. So we say that if kj, the corresponding bit of the key register is 0, then we are going to ignore. And if we are going to ignore, we will always assume that it's a match. That's why we make this value a 1 instead of 0. Now, let us put this all together then. So if you put it all together, then the match logic now will be mi would be equal to, now instead of finding only kj, here we saw it was just the product of x's, product of all the x's. Now it would be, it will be x1 plus k1 dash into x2 plus k2 dash, xn plus kn dash. Okay, and I can expand it even further to write x1 is equal to what? A1 f11 plus k1 dash, plus A1 dash f11 dash plus this k1 dash into x2 is A2 f12 plus A2 dash f12 dash plus this k2 dash. It goes on like this for the last one, that is an f1n plus an dash f1n dash plus kn dash. So this again in short form we can write it like this: mi is equal to the product over all j going from 1 to n. Okay, how do we write it? Aj, Fij, or Aj dash, Fij dash plus Kj dash. So this, what we have arrived at now, this is the proper match logic for each cell of your associative memory using the argument register as well as the key register. Now, let us look at the circuit now. Let us look at the how we are going to implement this each cell of your associative memory. So I will have something like this. This is the circuit diagram. So first of all, I have a flip-flop. I will use a RS flip-flop here. Okay. So RS flip-flop is here. Then we have the input line here. Then we have a write here. This is the write signal. And this is the read signal. Okay. Now, I have two AND gates connected to the two inputs of the flip-flop. Okay. And how is this going to come from? So this one from here up to this. And then here I have an inverter. All right. So the input is connected to the R and the S. Okay. So if the input is 1, then it goes like this via the inverter. So this becomes 0. Okay. And this is the write symbol. This is the write signal. So the write signal goes to both the gates. Okay. So as you can see, so if the input is 1 and the write is 1, then that means value 1 will be written to the flip-flop. So to write 1 to the flip-flop, we will have to make the input here equal to 1 and the input here equal to 0. That's how the RS flip-flop works. So we have to do that. To do that, you can see this 1 is passing through the inverter and it has become a 0 here. This is a 1 here. So 1 and 0 is 0. So we get a 0 out here. And on the other side, the set side, S side, here this is a 1. Write symbol is 1. Write signal is 1. So 1 and 1, we get a 1. So S input is 1. R input is 0. So the flip-flop will store 1. Now, what about the read? In case of read, so this is the output, which is nothing but your Fij. Okay, this is basically the content. So here, this is the read signal. So from the read signal, this is going to be the output. Why we have used AND gate here? So let's see. Suppose I have a 1 here, that is the read is 1, and the bit here is 1 in this flip-flop is 1. Then 1 and 1, I get output. I get 1. Okay, and if the read signal is 1, and here I have an input of 0, that I mean the flip-flop contains 0, then 1 and 0 will give me 0. So whatever is there in the flip-flop, that is what I'm going to get as the output. So this is for the read and the write. Now this Fij, okay, in order to do the match here, this is your circuit for the match logic. This is the circuit for the match logic. So the match logic is going to take Fij. It is also going to read from Aj and Kj. Aj for the argument register bit and Kj for the match for the key register bit. So with this, so it will look at Fij, it will look at Aj, it will look at Kj. Remember our match logic function here. So AJ, Fij, AJ dash, Fij dash, and Kj dash. So it will look at these inputs and then it will give us the output of Mi. So it will set, or it will make this bit 0 for a corresponding bit in the match register. So this is one cell, this is one single cell of your associative memory. So like this, the entire associative memory, which we have seen here. Okay, so what we have seen is only this part, one cell. So like this, each cell of associative memory will have this logic, will have this circuit. And then corresponding to that, after that, there is the match logic circuit, which we will see in the next part.